Hello, Historical Geology students, and welcome to your lecture number 7. We're going to be talking about metamorphic rocks this time, and you'll probably be happy to know that I don't think this one is going to go on quite as long because metamorphic rocks are not as important to what we study in this class, but I want you to know what they are and what they're about and that they exist. And so probably I'm just going to be going on for maybe just half an hour, even something like that. So it should be a little shorter than normal. So metamorphic rocks are one of the 3 basic rock types, right? And we talked about sedimentary rocks last time. That's the really important one, and that lecture packed a lot of information into it, and you got to know it all. So everything I said in there is important, and it's all stuff you have to know. Because it's gonna come up again and again. Metamorphic rocks, though, are a little bit less so, but I just want you to have some basics about them. So let's talk about metamorphic rocks without further ado. So this kind of stunning, dramatic image of layers in the rock that are all contorted and twisted and messed up. It's very beautiful in a way. But it's very indicative that metamorphism has occurred because the rocks have been twisted and deformed. Okay, and you're going to find that deformation, that change in the original rock structure, that's really what defines a metamorphic rock. So metamorphic rocks, they're the last of the rock types we're going to talk about. And they are rocks that have been metamorphosed, they've been changed. So meta, whenever you hear that prefix meta means sort of or kinda. Metaphysics, for instance, basically means sorta like physics or kinda like physics. Morph refers to form or shape, right? So it's basically means that rocks that have changed shape, it's sort of a change to their shape is a way you can interpret that. So metamorphic rocks are rocks that have been modified due to high pressure and temperature. The oldest rocks on Earth, something you want to be very familiar with in this class since we're doing historical geology, we're studying old rocks, is the Acosta gneiss. It's over 4 billion years old. Gneiss, this word gneiss right here, it's not spelled N-I-C-E like a nice person, it's spelled G-N-E-I-S-S. It's a German word, and it refers to this banded rock you see in the beginning, with these deformed bands in it. This is a gneiss as well. Okay. So the Acosta gneiss is the oldest rock on Earth, oldest crustal rock. It's over 4 billion years old. Okay. So metamorphic rocks are rocks that have undergone a collection of solid state processes. The word solid state just means that the changes have occurred in the solid state, in the physical solid state. It hasn't melted, okay? Once you melt a rock, you are talking about an igneous rock, okay? So once melting occurs, then you're in the igneous category. But these are rocks that have undergone changes, really dramatic changes in the solid state, okay? Once you modify the original rock, by the way, the original rock is called the protolith. Proto means beginning, lith means stone, so it's the beginning stone, the beginning rock that you start off with. Without melting it, you change it, you're going to end up with a metamorphic rock. So it could be through high temperatures, high pressure, or it could be through hydrothermal fluids. But and any combination of those agents change your rock and change your protolith and change it into a metamorphic rock. There are different grades of metamorphism. Okay, you could have low grade, in which there are only slight changes, to high grade, in which very dramatic changes occur. Okay. And what is modified during metamorphism? Grain size, grain shape, the kind of minerals. There's also something that develops called foliation. Foliation is a preferred orientation to the grains, to the crystals in that rock. Where? Depends on the tectonic environment. Okay, and we're going to talk about the kinds of metamorphism you get in different tectonic environments. So, what kind of temperatures are we talking about here? Now, you remember that rocks are melting, basically around the 1200 degrees Celsius to maybe all the way down possibly to 600 degrees Celsius, but it kind of depends on water content, it depends on the pressure. I hope that you recall that as pressure goes up, so does melting temperature. Okay, so it's not like rocks just melt at one temperature. Okay, there's a whole range. Rocks melt anywhere from 600 to 1200 degrees Celsius. So there's kind of an upper level on what temperatures at which metamorphism occurs, right? So if it gets too hot, then we're talking about igneous rock. So usually metamorphism is going to occur in the 250 to 850 degree range. Okay, but it could be lower if you're talking about a wet rock, because wet rocks, water is always going to lower the melting temperature. So once you're talking about wet rocks, the water lowers the melting temperature, and they melt at a lower temperature. So that upper level is higher. So you could have metamorphism without melting the rock all the way up to 1200 degrees Celsius in a dry rock, depending on what the mineral composition is. Okay. But anyway, this is normal range, 250 to 850 in a normal rock, okay? Now, remember that it gets hotter as you go down into the earth, right? So temperatures at the surface are about 20-25 degrees Celsius, right? But once you start to get down maybe 5 kilometers, now remember how deep the crust is, right? The continental crust, about 30 kilometers, the ocean crust, about 5 kilometers. So once you get down to the bottom of the ocean crust, you're talking about 100 to 125 degrees Celsius. Once you get down to the bottom of the continental crust, you're talking more about 600 to 750 degrees Celsius. Okay, so which is well within the range of what kind of temperatures are needed to metamorphose a rock. Now, what about pressures, right? So pressure is kind of a weird thing. There are a lot of different units we use when we talk about pressure. For example, probably when you guys think that most people, the only pressure unit they really think of in terms of is pounds per square inch, PSI. So like if you ever measure the pressure in your tires, it'll usually say PSI, so pounds per square inch. Okay. The normal atmospheric pressure is 7 pounds per square inch. Inside of your tire, depending what kind of tire you have, but usually it's like 35 pounds per square inch. Okay. So it's really like maybe, 5 times greater pressure. The pressures that you get inside the earth are like tremendously higher. So like your car tire pressure is nothing compared to the pressures you get inside the earth. So we don't use PSI in geology. We use something called a bar, or we use something called a gigapascal. Okay. Atmospheric pressure, so the pressure that you are feeling right now, is conveniently defined as 1 bar. Okay, it is equivalent to 100. The actual like metric system unit we use here is a pascal. So that's equivalent to 100,000 PA or pascals. Okay, so the pressure under 10 meters of water, still only about 1 bar. Okay, it's not very much. But the pressure under 10 meters of rock is going to feel like about 3 bars. Okay, 3 times atmospheric pressure. The pressure that we get under 1 kilometer of rock is about 300 bar. Okay, and then the pressures that we get at like 5 kilometers, like at the bottom of the crust, the ocean crust, it's about 1,500 kbars, or that's about 15,000 bar. Okay, the pressure we get at the bottom of the continental crust, 30 kilometers deep, is about 9 kbar, 9,000 bars. Okay, so it's 9,000 times the pressure that we feel at the surface. Does that make sense? So just kind of give you some perspective on temperatures. Florida, 25 degrees Celsius. I could have put South Texas here too. I mean, that normal day, it's probably going to be probably right now as I'm recording this, it's about 25 degrees Celsius, okay? Inside of a gold mine, you're pretty deep down into the earth, you know, maybe you're a kilometer down. It's maybe 60 degrees Celsius. Okay. Inside of a pizza oven, it's about 350 degrees Celsius. And it's kind of funny because, you know, that's about like as hot as we're used to things getting. You know, maybe a pizza oven's like one of the hottest things we're going to be around, you know. But we're talking about really high temperatures in the earth. So right at the bottom of the continental crust, we're talking about like 600 to 750 degrees Celsius, way hotter than a pizza oven, right? Double the temperature there. Give you some perspective on pressures. So I mentioned at the bottom of the continental crust, we're talking about 9,000 bar, right? So 30 kilometers deep, we're talking about 9,000 bar, 9 kbar, kilobars, right? If you were to have 50 African elephants sitting on a chair, that would only be 2,000 bars, 2 kbars. It's really not that much, okay? By the way, another unit we use is called a gigapascal. Now, I already told you what a pascal is. So, you know, 1 bar is equivalent to 100,000 pascals. But a gigapascal is called a GPa, okay, like that. And it is equivalent to, one GPa is equivalent to, I'm going to put this, 1 GPa is equivalent to 10 kbar. Okay. So the pressure at 30 kilometers depth at the bottom of the crust, 9,000 bars, about 9 kbars. It's pretty close to 1 GPa, be 0.9 GPa. Okay, 1.9 gigapascals. So metamorphism, change of a rock, is going to occur under high pressures and or high temperatures. And what's going to happen is you'll get this suite of rocks that change in a progression, okay? So I'm going to show you an example of that. Now, as you know from sedimentary rocks, if we start out with mud, okay, mud can undergo diagenesis to become a shale, right? I hope you remember that from the last lecture. Now, if we start to increase the pressure and the temperature, let's say that shale gets buried deep within the earth. Maybe it gets down to a kilometer deep in the earth. Maybe it gets to 10 kilometers. Maybe it gets all the way down to 30 kilometers, okay, which can happen easily. Let's say it gets buried. You're gonna turn that shale into a rock probably you've heard of called slate. If you ever heard of like slate board, it's like a chalkboard, you know, it's a very flat, very sheety kind of rock. It's like breaks into these thin sheets. It's kind of neat. You know, it almost makes natural chalkboards. And people used to use it to like in England and Scotland to tile their roofs with, right? Now, increase the pressure and temperature, that slate is going to turn into a rock called phyllite. And phylite's a little shinier. It's got a little bit more sheen. Increase the pressure and temperature, you're going to undergo more metamorphism. You're going to kick up the metamorphic grade. You're going to turn into a rock called schist. And finally, once you get to the highest metamorphic grade that you can get before melting, you end up with a gneiss. Now, what happens in each of these is that there's going to be changes to the mineralogical content, so the mineralogy. The different minerals are going to appear. You're gonna start to turn those clay minerals, and I hope you remember I talked about clay minerals in the mineral lecture. You're going to start to transform some of those clay minerals into a mineral called muscovite, okay, which is a mica. So these are going to get more and more mica rich. Finally, those micas you're going to end up with mica plus quartz and feldspar. It's going to turn into, and you're going to get this banding. You see all this banding, kind of looks like a zebra. That's very indicative of a gneiss rock, okay? So that's called pressure solution, and it's a type of foliation that occurs very commonly with metamorphic rocks, and I'll explain more about that later. Think about limestone, right? We start off with the bodies of marine organisms, shells, and tests from microplanktonic organisms. It undergoes diagenesis, remember, and you create a limestone. If that limestone undergoes intense heat and pressure, it eventually turns into a marble. Okay, so all the beautiful marble which we use for building, is actually metamorphosed limestone. Okay, so that's what it starts off with. Similarly, if you start off with a sandstone, it undergoes heat and pressure, metamorphoses, it turns into a quartzite. So some of the first changes, let's talk now, that's an introduction to metamorphic rocks and metamorphism, heat and pressure. Let's talk about what specifically occurs during the process of metamorphism. So one of the first changes that occurs is something called recrystallization. This is when there's a change in the size and the shape of the grains, but you don't change the actual minerals that are there. So a good example of this is the sandstone turning to quartzite. So little tiny sand grains will combine together. They'll actually kind of coalesce together and become larger grains. And they're also going to become this sort of the sort of space in between the grains, the pore space, is going to disappear, because as you can imagine, once you kick up the pressure really high, you're going to get rid of pore space, right? Once you squeeze it, you're going to squeeze all the pore space out. So that pore space is going to disappear, and you're going to get this suite of interlocking grains that look just like this, right? It almost looks like a jigsaw puzzle. So those interlocking grains are going to grow, they're going to get larger, they're going to lock together, and you get this new kind of coarser grained rock called a quartzite. Okay? So it might interest you to know that larger crystals are always more stable than smaller crystals. So there's always going to be a preference to grow crystals larger and larger and larger. It just takes time. Okay, so that's kind of how recrystallization works. So minerals are usually going to get larger. Crystals are going to grow and get larger. You'll notice that a lot of metamorphic rocks are really beautiful, and they're really beautiful because they've undergone that recrystallization. The crystals have gotten larger, and it looks more sparkly, basically. To put it bluntly, it just kind of looks more sparkly. Larger crystals are always more pretty than smaller ones. So another change that can occur are phase changes. Okay. Phase changes are when you change the packing arrangement of the atoms. Now, I've already presented some examples of that before. Diamond and graphite, remember, those are polymorphs. So diamond and graphite are the same in terms of chemistry, right? They're both just pure carbon. But if you kick up the pressure, right, high pressure, you can change the crystal structure of the graphite to that of diamond, which is a very different mineral, but it has the same chemistry. Okay, so you're just changing the packing of the atoms, and basically as you kick up the pressure, remember that as pressure increases, the rock is always going to try to find ways to get smaller and more compressed and get rid of its excess volume, right? So it's going to get rid of pore spaces. It's going to get rid of any bubbles or holes in the rock. It's going to also switch from kind of high volume phases, high volume minerals like graphite, to low volume minerals like diamond. Diamond is more compressed, has a higher density than graphite. Okay. Another example of that, coesite is denser than quartz. So quartz will change sometimes to coesite, which is, again, they're both SiO2. They're polymorphs, but coesite is denser. So at high pressure, you get coesite instead of quartz. Marble has a denser packing than just calcite. Okay. Also, you get what's called neocrystallization, means new crystallization. So you get new minerals. So at a certain point, once the pressure and temperature increase enough, different minerals are going to be more stable. Okay, and so example of this is quartz and dolomite will combine to give you pyroxene, and it'll give off CO2 gas actually. So that's an example. You have a whole new mineral created from the two old minerals. Okay, so that's called neocrystallization. Another thing is called pressure solution. So in a lot of cases of metamorphism, there is a kind of the pressure is coming from a certain direction. Sometimes it's coming from all directions, but sometimes when there's like two tectonic plates, squeezing together. Here's my tectonic plates squeezing together, right? And you're going to have mountain building here as the plates squeeze together. There's going to be kind of like a direction to the stress, a direction a preferred direction that the pressure is coming from. And in those cases, it's going to squeeze grains. So this is called a differential stress. It means that it's not equal in every direction. There's a preferred direction. And what that's going to do is it's going to take spherical grains and make them more elliptical like this and squeeze them out. Okay? So there'll be shortening in one direction and grain growth in the other direction. Okay? You also get plastic deformation, in which things will be squeezed and shortened and just get elastically squeezed. So pressure solution is a little bit different because you'll get dissolution in one direction and you'll get grain growth in the other direction. This is actually plastic deformation, when it's actually being squeezed and again changing the shape when there's differential stress. Okay. Now, so those are the different changes that can occur in a rock. What about the agents of metamorphism? What causes metamorphism? So as I mentioned many times already, the agents of metamorphism are temperature, high temperature, and high pressures, along with fluids, hydrothermal fluids. They're very effective agents of metamorphism. Okay, so let's talk first about temperature. Let's talk about the case where you have relatively high temperatures but relatively low pressures. So that is called contact metamorphism. That's when you have relatively high temperatures, relatively low pressures. So for example, when a plutonic rock body is intruded into the country rock, into the native sandstones and sedimentary rocks that are near the surface, we call those the country rocks. When a pluton is intruded, it's very hot, right? So you have a magma chamber forming, and the zone around it is going to get hot. So there's going to be what's called this zone of contact metamorphism surrounding the pluton that metamorphoses the country rock surrounding the pluton. So good example of this, if you have a granite dike, which is a dike is kind of like a vertical plane of magma that has been intruded. Okay, instead of a kind of a magma body, like a big bulbous magma body, it's formed in a plane. Like you can almost think of it as a line. Okay, so imagine you have a granite dike. The country rock surrounding it is going to be metamorphosed into a rock called hornfells. So this is baked mudstone. Okay, it's mudstone that is still a mudstone. It's still like shale, but it has been subjected to high temperatures. Not quite enough to melt it, but enough to bake it and change the kind of texture and make it into a metamorphic rock. So contact metamorphism produces a new metamorphic rock called hornfells. Okay, so you should have that name kind of in your mind, connected with contact metamorphism, hornfells. Okay, pressure is another agent of metamorphism that changes our rocks, right? So high pressure can cause recrystallization, can cause neocrystallization, can cause all the pressure solution and things like that. All right, so sandstones, right, turn to quartzite. That's what a microscopic image of sandstone looks like compared to a quartzite, and you can see how the grains have become interlocking. They become much larger. This is all quartz, by the way. All this stuff you see is quartz. Okay, so you get small grains plus the cement recrystallizing to form this quartzite. Okay. Temperature and pressure can work together too. So sometimes you get just high pressure, sometimes you get just high temperature, but very often you get high temperature and pressure. Okay. And what's kind of cool is that metamorphic rocks, you'll find that we can often figure out exactly what set of temperatures and pressures a metamorphic rock was exposed to by its mineralogy. Okay, so a good example of this is how we can figure this out. And of course, there are many ways, but this is just an example. Polymorphs of Al2SiO5. So Al2SiO5 forms a few different minerals called, I'll give you three different minerals called kyanite, sillimanite, and andalusite. Okay, these are all metamorphic minerals. So there's a picture of each of them: Andalusite, kyanite, sillimanite. They all have the same chemistry, so they're polymorphs. Now, what we find is that these are stable under a certain area of temperatures and pressures. Andalusite is stable at relatively low pressures, 0.2 GPa. Okay, so that's 2 kbar up to this point, but you can see that it changes with temperature. Okay, sillimanite is kind of the high temperature, stable at higher temperatures. Okay, whereas kyanite is the one that's stable at relatively high pressures and relatively lower temperatures. But it's kind of cool because, you know, if you find kyanite in a rock, you know that it had to form somewhere in this field, right? Had to form somewhere in this kyanite fields. And you can see this is a temperature pressure diagram, right? So you have temperature on the bottom axis, you have pressure on the vertical axis, and it gives you an idea, you know, depending if you find Andalusite, kyanite, or sillimanite, it gives you an idea about what the temperature pressure regime must have been. Okay, so pressure and temperature can change your minerals, can form these different polymorphs, right? Polymorphs are minerals that have the same chemistry but a different shape, different form and packing of atoms. Okay, right. So the Al2SO5 minerals, right? The we call them aluminosilicates, form that. Andalusite, kyanite, sillimanite are polymorphs. Diamond and graphite, as I've mentioned many times, are polymorphs as well. Okay, so right, temperature and pressure can change our limestone, right, into marble, and does that through recrystallization. So another thing is compression and shear. So shear is when you have the compression coming not from equally from every angle, but from a certain direction. Now, what this does is it causes something very common in metamorphic rocks called foliation. Foliation is a preferred orientation to the grains. So you can see how under stress from a certain direction, it's going to squeeze the grains, and there's going to be a preferred orientation to the grains. So this is a metaconglomerate. So it started off as a conglomerate with these perfectly round pebbles and cobbles, but you can see now that they are squeezed together from a kind of preferred orientation. You can also see how grains flatten and they rotate. That's all examples of foliation. There's a preferred orientation to the grains and preferred orientation to the crystals in this rock. Okay, so that is all a response to pressures from a certain, or stress from a certain direction. Okay, which is, like I said, is very common when you have tectonic plates colliding. You know, the pressure, the stress is coming from that certain direction of collision, right? The final type of metamorphic agent is hydrothermal fluids. So these, you know, are hot fluids that are constantly flowing through rocks. You might know that there's groundwater, of course, and you know, when you get groundwater very deep, it becomes very hot, and it's going to pick up a lot of different dissolved solids, dissolved minerals, and those become very effective agents of metamorphism. Okay, so hot water with dissolved ions in it, very good at changing the chemistry of the rock. Okay, so here again is another pressure temperature diagram. So pressure's on the vertical, and you'll notice that zero pressure is at the top instead of the bottom. So it's kind of going with depth, right? The deeper you go down below the earth, the higher the pressure. Temperature is on the horizontal axis here. So and as you know, this line here kind of shows how the temperature of the earth changes with depth, right? So if you're going to get buried in the earth, right, from maybe about this point, there's no metamorphism. But as you continue going down, you're going to have low-grade metamorphism around 300 degrees Celsius and maybe 2 kbar. You're going to go to intermediate grade metamorphism when you get to 500 degrees Celsius and maybe 5.5 kbar. And you're going to get to high-grade metamorphism once you get to 700 degrees Celsius and around 8 kbar. Okay, and then anything beyond that, once you get to this curve, this is the melting curve. So once you intersect with that, melting starts to occur. And so that is going to be no longer a metamorphic rock. Okay. This is the wet melting curve. Remember I said that wet rocks are going to melt more easily. So here's a wet melting curve right here. Here's a hot melting curve. Or I'm sorry, a dry melting curve. Okay. So contact metamorphism. Let me erase everything on here. Whoops. Okay, so if you follow this PT path, this pressure temperature path, this is called just normal, like basically what would happen under just normal burial. Okay, that's called mountain belt metamorphism because it's just kind of burial metamorphism. Sometimes this is called regional metamorphism, and it's high temperature combined with high pressure. This, I'm going to use a different color. I'm going to use a red color for hot temperature. If you follow a PT path like this, notice that you are increasing the temperature without increasing much of the pressure. So at this point here, you're only maybe at 1 kbar, but you're at like 800 degrees Celsius, okay? So that would be a high temperature but low pressure metamorphism. We call that contact metamorphism. The third type of metamorphic regime is when you have high pressures, but you have relatively low temperatures. So you call this subduction metamorphism in that case. Okay, so this is the kind of metamorphism that we see in subduction zones. So again, this is just the different what are called metamorphic fascies. So these are sort of different regions of pressure temperature space in which they're useful to refer to these different fascies in order to give us a sense of what the pressure temperature actually is. So this is, for example, called the Hornfels fascies. So you know a Hornfels fascies is going to be high temperature, low pressure. This is going to be called the blue schist facies, and that is going to be high pressure, low temperature. Okay, things like this are called, like this one for example, is called the green schist facies. Okay, you can see that's sort of moderate temperature, moderate pressure, et cetera, et cetera, et cetera. So I'm not going to be using these terms too much in the class, but sometimes you'll run across them, and I want you to be familiar with it. And just know that basically what metamorphic facies are is they're telling you what the pressure temperature regime is that rock, that original protolith, was subjected to. Okay. So that's all I'm going to talk about here. Let's just kind of quickly review what I've mentioned. So what is metamorphism? Solid state formation, right? Solid state changes to a protolith that involve recrystallization, phase changes. And you should be familiar with the different kinds of metamorphic rocks. Okay, you should know, for example, you should know slate, schist, phyllite, and you should know also gneiss. You should know limestone. You should know that you should know that marble comes from limestone. Okay, you should know hornfels. You should know also blue schist. Blue schist is a subduction type rock that is high pressure, low temperature. Okay, when are metamorphic rocks formed? They're formed under high temperatures, high pressures, at depth. They involve fluids, sometimes can involve compression, shear, differential stress coming from one preferred direction. What causes, so also you should know foliation, right? You might want to read more about that in your book. And they have a whole chapter you should read on metamorphic rocks. But foliation is a preferred orientation to the grains. Okay, it's going to make kind of unequal grains, inequant grains that are squeezed in one direction from differential stresses. Okay. Also, you should know about metamorphic intensity, the metamorphic grade, right? So under a normal geotherm, you're going to go from the green schist facies to the amphibolite facies to finally the granulite facies. Okay, you're going to be going under high pressures and high temperatures. Under a normal geotherm, you're going to change a mudstone, for instance, from a slate to a phyllite to a schist, finally to a gneiss. Okay, so this would be the normal kind of progression, normal progression of metamorphic rocks for a basalt, for a mafic rock. This would be the normal progression for the different kinds of rocks you'd find under a normal geotherm for a sedimentary rock in which burial regional metamorphism is occurring, or mountain belt metamorphism. A hot geotherm that's low pressure and high temperature is going to give you a hornfels. A cool geotherm is going to give you a blue schist. So that means cool geotherm means high pressure but relatively low temperature. Okay, so I know there's a lot of stuff here. I mean, you don't have to be a master of all of it, but I could just kind of like, I know it can be kind of overwhelming because it's a lot of information, and you don't have to, like I said, you don't have to be a master of it. But for example, like, you should be able to tell me what rock is generated by metamorphism of a limestone, and the answer to that would be marble, right? You should be able to tell me what kind of rock is formed by contact metamorphism. That would be a hornfels. You should know, like, what kind of what for example, like, which is higher grade metamorphic rock, a gneiss or a slate. You should know a gneiss is a higher grade type of metamorphism than a slate. Okay, so things like that. So if that sounds reasonable to you, that's kind of what I'm looking for. I mean, you should know things like, I could ask you, about agents of metamorphism, about temperature and pressure. Maybe you should be good to know, like, what kind of temperature and pressure ranges we're usually talking about. Okay, so I think that's all I want to hit on here. Here are some, like, specific exam questions. So blankety blank is a place where rocks are probably being subjected to high or to contact metamorphism. So you're looking for something that's going to have high temperatures but low pressures, right? So a mile under Mount St. Helens, 15 miles under Japan, a mile under Wisconsin, a mile under Mount Everest. Okay, so Mount Everest. So we're looking for high temperatures, low pressures. So Mount St. Helens is a volcano, right? So that's going to be high temperatures. Japan is also a volcano. Okay, there's also volcanoes in Japan. There's no volcanoes in Wisconsin. There's no volcanoes in Mount Everest. So you know that those are out. So 15 miles under Japan, though, is going to be high pressure, high temperature. A mile under Mount St. Helens will be high temperature, low pressure. So it's going to be A. Okay. What's the correct metamorphic sequence of increasingly coarser grain sizes? So again, you're looking for the rocks being in the right order of metamorphic grades. So phyllite, slate, gneiss, schist, no. You want gneiss to be the highest grade. So maybe this one, let's look at slate, phyllite, schist, gneiss. That's correct. So this one is B. Okay. Blankety blank is a metamorphose equivalent of limestone. That's simply marble. Okay. So hopefully that seems reasonable to you. That's the end of the lecture, and I hope you have a good week, and I'll talk to you next time.